This is AQA A-Level Chemistry. We are on the Year 12 Alkenes topic, and this is video number 3. In the last video, we looked at electrophilic addition mechanisms using Hbr, Br2 and H2SO4. In this one, we're going to dig into that a little bit more to look at what can happen with asymmetric alkenes. And we're going to consider where there are major and minor products. So in the first instance, I want you to have a think about what would happen if Hbr reacted with propene. And there's actually 2 different routes it can go, and it would be good for you to see if you could go through both of them and actually see if you can work out what the major and minor products would be. So I will start by drawing out my propene, and you can see that there, and my Hbr. Mechanism identical to the one we looked at in great depth on the last video. So I've got my electron rich double bond, I've got my delta positive hydrogen, so I'm going to get a curly arrow that shows the movement of electrons from electron rich to electron deficient. I've essentially formed a bond between the C and the H, which means the CBr bond must break, and those electrons go from the bond into the Br. Now at this point 2 things can happen, because the H could go onto the first carbon, or it could go on to the second carbon. And that means that our positive carbocation could be in the 1 position or the 2 position. And that then means that the Br minus could attack or will attack, and we would end up with either 1 bromopropane as the Br minus joined onto here, or 2 bromopropane as we went on to here. Now, the major product in this case is 2 bromopropane. 1 bromopropane would be the minor product. We would get far less of it. And the reason for it, and I'm going to give you a chance to think about this on future tasks on this video, but the reason for it is that 2 bromopropane is formed via a secondary carbocation intermediate. It's secondary because the carbon that's positive has 2 alkyl groups connected to it. And that's more stable than a primary carbocation. This is a primary carbocation. It has 1 alkyl group connected to it. And we can talk a little bit more about the inductive effect that causes that later on. But something formed by a secondary carbocation intermediate is more likely to happen than a primary because secondary is more stable. So let's take that on board, and we're going to go back and revisit some of these key bits. But if I'd done that with Br2, why would it not matter? And if I go back to this mechanism, if we consider if I'd had a Br and then added a Br, or if I'd added a Br and then added a Br, they would both come out as 1,2-dibromopropane. So you're adding a Br to both sides of the double bond. So we're not going to get any difference at all. Now we're going to dig in a little bit more now about what primary, secondary and tertiary carbocations are. So based on what we've discussed, can you have a go at classifying these? In the first instance, I'm going to look at the top 3. We have got this carbon is surrounded by, there's an ethyl group, a methyl group and a methyl group. So that's 3 alkyl groups, and that means that it's tertiary. This one is primary because there's 1 alkyl group connected. This one's also primary. There are no alkyl groups, but we're not going to go lower than primary. For the next 2, the carbon that's positive has 2 alkyl groups connected, so it's secondary, and the carbon that's positive here has 3, which makes it tertiary. And the final 2 examples, this one is secondary, you can see the highlighting, and this one is primary, there is 1 alkyl group connected. So what about the stability of primary, secondary and tertiary carbocations? What do we think the order is going to be? Well, I've already spoken about it earlier in the video. Tertiary is the most stable, primary is the least stable. Let's have a quick look at why, about what's actually happening here. I've drawn out my tertiary carbocation with 3 alkyl groups around the positive carbon, my secondary and my primary. And we have a phenomenon called the inductive effect. Now, because this is positive, it attracts electrons, it draws them in. And on here, it's got 3 alkyl groups to draw them in from. This only has 2 and this only has 1. Remember that a hydrogen has only got 1 electron, so there's minimal impact as they're pulled in. Now, because I've got so many more electrons being pulled in, it actually makes this slightly less positive. And that means it's going to be less susceptible to attack, and that makes it more stable. And it essentially means it can exist for longer, allowing the bromine or the SO3H-, the bromide I should say, or the OSO3H- to come in and attack. So, the major product is formed via the more stable carbocation intermediate. So I want you to pause, have a go at this one. Why would we end up with the major and the minor product that we have here? And let's draw out the mechanism. Let's go through. I've got my propene drawn out. I've got my HOSO3H drawn out. My first arrow is going to go from the electron-rich double bond to the delta positive hydrogen. That means the HO bond is going to break, so those electrons move down to the O. And again, at this point, we split off in 2 potential routes. I can end up with my second carbon is positive, and here I've got the example where my first carbon is positive. Now let's classify those carbocations. This one is primary. It has 1 alkyl group connected to it. This carbocation is secondary. It has 2 alkyl groups connected to it. And because this is formed via a secondary carbocation intermediate, remember the OSO3H- would come in to make the propyl hydrogen sulfate, that would be the major product when this attacked. And remember, this could go on to be hydrated. That would give us propan 2-ol. That would give us propan 1-ol. Propan 2-ol would be the major product. Again, let's remember the wording here because it is formed via a secondary carbocation intermediate, which is more stable than the primary carbocation intermediate. Finally, on this video, just to finish off, have a think about this question. So I'm not going to go through the mechanism in full here. I'm going to ignore the mechanism and go to the carbocations that would be produced. And it could be that the positive ion was on this carbon, or it could be that it was on this carbon. But these are actually identical carbocations. They're simply mirrored. I've flipped them over. So we're not going to get different products. We are going to end up with our OSO3H- going on to the second carbon, which means after hydration, our OH would be on the second carbon, which means both of these would give us butan 2-ol. And it's important to remember that we only consider major and minor products when we have an asymmetric alkene. This is symmetrical. You can see the symmetry of the CH3C, the CH3C. We didn't have that symmetry with propene. That takes us to the end of this video. Thank you for listening and goodbye.